Quasi-empiricism in mathematics. Quasi-empiricism in mathematics is the attempt in the philosophy of mathematics to direct philosophers. Of concern to this discussion are several topics: the relationship of empiricism, see Penelope Maddy, with mathematics, issues related to realism, the importance of culture, necessity of application, etc. Primary arguments. A primary argument with respect to quasi-empiricism is that whilst mathematics and physics are frequently considered to be closely linked fields of study, this may reflect human cognitive bias. It is claimed that, despite rigorous application of appropriate empirical methods or mathematical practice in either field, this would nonetheless be insufficient to disprove alternate approaches. Eugene Wigner, 1960, noted that this culture need not be restricted to mathematics, physics, or even humans. He stated further that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research, and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement. Wigner used several examples to demonstrate why bafflement is an appropriate description, such as showing how mathematics adds the predictive ability in the sense of describing potential phenomena prior to observation of such, which can be supported by a mathematical system, would be another example. Following up on Wigner, Richard Hamming, 1980, wrote about applications of mathematics as a central theme to this topic, and suggested that successful use can sometimes trump proof, in the following sense: where a theorem has evident veracity through applicability, later evidence that shows the theorem's proof to be problematic would result more in trying to firm up the theorem. Hamming had four explanations for the effectiveness that we see with mathematics, and definitely saw this topic as worthy of discussion and study. We see what we look for. Why quasi is apropos in reference to this discussion. We select the kind of mathematics to use. Our use and modification of mathematics are essentially situational and goal-driven. Science, in fact, answers comparatively few problems. What still needs to be looked at is a larger set. The evolution of man provided the model. There may be limits attributable to the human element. For Willard van Orman Quine, 1960, existence is only existence in a structure. This position is relevant to quasi-empiricism because Quine believes that the same evidence that supports theorizing about the structure of the world is the same as the evidence supporting theorizing about mathematical structures. Hilary Putnam, 1975, stated that mathematics had accepted informal proofs and proof by authority and had made and corrected errors all through its history. Also, he stated that Euclid's system of proving geometry theorems was unique to the classical Greeks and did not evolve similarly in other mathematical cultures in China, India, and Arabia. This and other evidence led many mathematicians to reject the label of Platonists, along with Plato's ontology, which, along with the methods and epistemology of Aristotle, had served as a foundation ontology for the Western world since its beginnings. A truly international culture of mathematics would, Putnam and others, 1983, argued, necessarily be at least quasi-empirical, embracing the scientific method for consensus if not experiment. Imre Lakatos, 1976, who did his original work on this topic for his dissertation 1961, Cambridge, argued for research programs as a means to support a basis for mathematics and considered thought experiments as appropriate to mathematical discovery. Lakatos may have been the first to use quasi-empiricism in the context of this subject. Operational aspects. Several recent works pertain to this topic. Gregory Chaitin's and Stephen Wolfram's work, though their positions may be considered controversial, apply. Chaitin, 1997/2003, suggests an underlying randomness to mathematics, and Wolfram a new kind of science, 2002, argues that undecidability may have practical relevance, that is, be more than an abstraction. Another relevant addition would be the discussions concerning interactive computation, especially those related to the meaning and use of Turing's model church, Turing thesis, Turing machines, etc. These works are heavily computational and raise another set of issues. To quote Chaitin 1997/2003, now everything has gone topsy-turvy. It's gone topsy-turvy not because of any philosophical argument, not because of Gödel's results or Turing's results or my own incompleteness results. It's gone topsy-turvy for a very simple reason: the computer. 96. The collection of undecitables in Wolfram, A New Kind of Science, 2002, is another example. Wegner's 2006 paper Principles of Problem Solving suggests that interactive computation can help mathematics form a more appropriate framework empirical than can be founded with rationalism alone. Related to this argument is that the function, even recursively related ad infinitum, is too simple a construct to handle the reality of entities that resolve via computation or some type of analog n-dimensional